Alrighty, my friends, welcome back to probably the last video of this section, just to kind of keep things rolling right on through. So what I want to talk about now and really hone in on is this idea that carbon dioxide can now change the pH of water. And maybe you've heard of pH before, especially if you work in like the service industry where you have to have sanitizer water and you have to check the pH to make sure that there's a proper amount of sanitation in there, or anything along those lines. I worked for Starbucks a really long time ago, and like they are really in there on the procedures and checking everything. So I was very familiar with using those pH strips. Or if you're into stuff like fermentation, whether it be like kombucha or beer or wine or kimchi or sauerkraut, anything like that, or pickling stuff, very similar to fermentation, but a little bit different. But so with that, it's always best to test your liquid to know the pH of it. So when we consider the pH scale, it goes from 0 to 14, with 0 being very acidic and 14 being very basic. So here is a graph showing the pH of seawater and showing how acidic something is or is not. So pure water is right here in the middle. So that's about 7. And so if we were to consider a healthy ocean is at about 8.2. The pH overall does vary throughout all the oceans at all depths. So this means that it's not the same everywhere. There's places where, where there's less CO2 uptake, most specifically in the surface ocean waters, not like the surface open ocean, not the surface of the ocean like next to Hawaii or something like that. So we have to consider the open ocean. And there's a whole heck of a lot of open ocean, right? So what's kind of wild here is, looking at some of these examples, and I say this wrong all the time about like acidic is lower values and basic is higher values. So if you find yourself kind of getting mixed up with all of that, me too. So some common examples of stuff that may be acidic would be like battery acid, of course, or lemon juice or vinegar, orange juice. And then acid rain in an acidic lake, that's at about 4.5 pH. This is a really big concern right now for the water systems in East Palestine, Ohio, because of the train derailment, which, by the way, they fixed the stuff and now more trains are rolling on through East Palestine. Anyways, and then things like bananas, clean rain. This is a really important distinction to make here as well. Clean rain, which arguably a lot of the rain that we get these days is not very clean. And a healthy lake is at about 6.5, right? So that's two points different between an acidic lake and a healthy lake. And then things that are a bit more neutral or basic, and this one is where it like kind of is hard for me to remember, because bleach is like, it smells acidic. Like I love the smell of bleach. I love that clean, super clean smell. So that's why it's harder for me to remember that bleach is basic. Or liquid drain cleaner, similar sort of thing. It has that really chemically sort of smell. So I have to like remember that those are basic. Fun little factsies, by the way, if you're ever not feeling very good in your tummy, if you put like a teaspoon of baking soda in a pint of water, mix it up and chug it down, that's like I don't want to say poor man's way of Tums, but it's an easy way to help kind of balance out the pH in your tummy. So you may see this and you're like, okay, pure water is 7, a healthy ocean is 8.2. So like, making a point or 2 points different, how can that like alter the entire chemistry of seawater, and why can that be a problem? Well, think about the last time that your tummy was upset, and maybe you had like the flu or food poisoning, or you were violently hungover or whatever. When your tummy was upset, that was only a change of maybe 0.1 or 0.2 of the pH of your tummy. So that's you, right? And that's on a super small scale. So you can imagine the havoc that it could wreak on a larger scale. So the reason this is a problem, or like how this can change the pH, is through this carbonate system. So there's a lot of chemical reactions that happen in the water with various molecules. So I know that this schematic is a little bit kind of hard to digest initially, but basically the idea here is if you add CO2 as a gaseous state into water, dissolves into water, so now it's in the liquid state with water, that can turn into carbonic acid. So CO2 plus H2O gives us H2CO3. And then that can turn into bicarbonate, so the hydrogens kind of, they separate, and then that can further break down into just regular carbonate. And this process of precipitation and dissolution can happen. So if the seawater pH is high, meaning above 9, then there's too much carbonic acid. So this shifts over here to the right-hand side. So there's more carbonic acid. If the seawater is low, that means that there's more carbonate in the water than the other molecules. So most of which in our oceans of dissolved CO2 exists as bicarbonate. The reason that carbonic acid is bad is because it breaks down calcium carbonate. So it very efficiently breaks it down, meaning, you know, there are creatures in our oceans that really love calcium. I mean, you really love calcium. We love calcium. What does calcium build for us? Big, strong bones, right? We're all supposed to be, you know, drink your milk for breakfast so you have strong bones when you get big and strong, you know, like that's something that I was always taught, at least when I was a kid. So it's really quite, you know, the animals that have shells also really like calcium, right? So it can be kind of not great for our shell-making critters that live in the oceans, like mussels, clams, oysters, cuttlefish, coral. Coral's a huge one. Sea stars, urchin, like all lobsters, anything that has a shell needs calcium. And so if you're taking the calcium away, you're effectively completely changing the landscape and completely changing the biological makeup of these different animals. So where does that come into play for us? Why the heck should we matter about all this? Well, because if we're putting more CO2 into the atmosphere and the ocean is intaking a lot of CO2, then we're effectively, we're forcing this shift to the right. We're forcing more carbonic acid into the oceans than is naturally there in this whole process anyway. So how has CO2 been changing? Well, here we are. This is what's called a Keeling curve, and these are measurements of carbon dioxide from the top of Mauna Loa on the Big Island of Hawaii. It's a really, really great space to obtain CO2 concentrations from around the world, because if you think about where Hawaii is, it's in the middle of the frickin' Pacific Ocean. So it's not close, directly next to a city or a big mass of land, right? It's basically the perfect way to get the overall average concentration of CO2 that's not being biased in any way or another. So look at this pattern. What do we see? Take a pause. What do you see? Oops. You hopefully are seeing this pretty stark increase in the CO2 concentration since we started taking measurements there in 1959. So if we're constantly adding more CO2 into the atmosphere, then the ocean is going to start intaking that CO2 as well. So how do you think, this would impact ocean pH levels? I mean, it's a pretty easy answer there. That means that we're increasing the CO2 in the oceans, which is then making our oceans more acidic. So this image here is looking at, one more thing I want to touch on real quick is you see these little oscillations in here as well, right? Think about the process that uptakes CO2. Photosynthesis, right? So in the spring and summertime, trees and plants are all like, look at me, look at my leaves, hello, I'm going to intake all of this CO2, woohoo. And in the fall and winter time, those leaves go away, the tree goes dormant, and then it's no longer intaking CO2, right? Makes sense. So when you have those natural processes of intaking and releasing CO2, then that's where you're going to get this seasonal sort of variation here. And actually, one thing that I wanted to show really quick is the website where you can get all of this information. So this is the full record, and I do also just want to say Mauna Kea is now been where they've been taking CO2 observations because, the Mauna Loa started erupting. So they had to move the instruments to a different location so that that's not biased information. But what's really cool about this website is you can see information for the past 2 years, the past year, 6 months, 1 month, and 1 week, right? So you can see where this past 6 months, where this little break was, where Hawaii was like, I'm going to explode a little bit. And then we can also see 1700 to present, obviously very stark increase there. The last 2,000 years, the last 10,000 years, and we can go even further to the past 800,000 years. So we're able to track this pretty dang accurately through ice core information from various parts of Antarctica, because the atmospheric concentrations are frozen in those bubbles, in those air bubbles that are in the ice. So because of that, we have a pretty dang accurate representation of CO2 concentrations, and we can see that we haven't had this high in CO2 in the past 800,000 years. So could be of concern. So continuing on for just a few. So this is looking at how anthropogenic CO2 has changed in annual mean sea surface pH since the pre-industrial period and to today. So the scale here doesn't even have any color in the positive. It's all negative. And so what we can see is that there has been a decrease in surface seawater pH all over the world. But really, to me, things that stick out are right off the coast of Greenland and Iceland up here in the northern hemisphere, and also in the southern hemisphere. So the Atlantic Ocean seems to be taking the biggest hit for whatever reason. So it's really not that great. And then, again, the increasing acidity makes it really hard for organisms to construct hard calcium carbonate forms like shells or coral. And so here is some pictorial evidence of what can happen to a shell that is introduced to water that is too acidic for the calcium to stay. So it's breaking down with each given image. So not great, not awesome. It's actually a pretty big issue here. And some critters are more adept to this change than others. And it even can impact just regular fish too, not just ones that make shells. So overall, there it is, chapter 5. We've already breezed through a whole nother chapter, which is pretty wild, right? So I told you that these two would be quick. And then we'll jump into the atmosphere. So things that we covered in this chapter include what salinity is and the average value for the oceans, how and why salinity varies around the surface of the oceans, the gases that are in the ocean versus the gases that are in the atmosphere, and then finished up with a carbon cycle, biological pump, and ocean acidification. So with that, we'll go ahead and pause, and then when we come back together in class in person, then we will review and go through the rest of the stuffs. All right. Well, thank you all again so much for watching, and I'll see y'all on the flippy floppy. Bye.